Case study 2.3 looks at calculating energy yield from chemical bonds, and it applies this to the combustion of fossil fuels as an example. But the most remarkable thing about case study 2.3 is that it points out something of fundamental importance, and that is, independent of the molecular structure, the strength of hydrogen-hydrogen single bonds remains invariant to the structure of the molecule. That's the same thing with a carbon-oxygen single bond or a nitrogen-nitrogen triple bond. These bond strengths are a very good approximation for the bond strength coupling atoms within any molecular structure. And this turns out to be very important for calculating the energy release from a chemical reaction, because I can take the reactants, determine the strength of their bonds, do the same thing for the products, subtract the two, and I can calculate the energy production from a given chemical reaction. This is very, very valuable in practice. So let's see how this works. Let's take a look at the oxidation or the combustion of fuels. And we can start with hydrogen, because hydrogen reacts with oxygen to form water, and we can actually burn hydrogen in all sorts of different devices to produce energy, and the only product is water. That turns out to be very important. If we look at methane, or natural gas, methane is comprised of carbon-hydrogen bonds, but there are 4 of them that, when combusted with oxygen, form CO2 and water, the 2 thermodynamically stable products. When we contrast that with petroleum, petroleum is a chain of carbon atoms, and that chain of carbon atoms has hydrogen atoms bonded to it. So I can couple this into a joining carbon, and petroleum are long chains of these. So we have 2 carbon-hydrogen bonds for petroleum. Coal, in sharp contrast, is created by linking carbon in different structures, but it only has 1 hydrogen coupled to each one of those carbon atoms. So when we combust this, it turns out that the energy yield per unit of emitted carbon, the energy release from methane per unit of carbon release is much higher than it is for coal because of that structure. But again, we can calculate the energy yield from these reactions very quickly because we know what those bond strengths are for both the reactants and the products.